Hi there. So I think in the previous videos we've sort of introduced the idea of complex variables, and in particular in the last video we talked about addition of two complex variables and what that means geometrically, and we found that it's the definition coincides with that of the parallelogram law for vector addition. So one of the things we need to do now is think about what multiplication of two complex variables means on the complex plane. And in fact, this is a very, very important idea which will help us a lot in building intuition for what complex derivatives and integral actually mean geometrically. So this idea of the product of complex variables and its geometrical interpretation is actually extremely useful in the study of complex variables and functions. So if you recall, the way we defined multiplication of the product of two complex variables, so let's say we have z1, which is x1 plus I times y1, and then z2, which is x2 plus I times y2. Then their product z, which is z1 times z2, is x1 plus I y1 times x2 plus I y2. And this we define as, in the sense we in order to proceed with this, taking this product, we said that we'll just use I as a symbol. We can commute I with a real variable and use all the sort of properties that we associate with real numbers, and so the algebra then works out to be x1 times x2 plus I y2 plus I y1 times x2 plus I y2, and this gives us x1 x2. This is the first part coming from here, and then we have I times y1 times I times y2. Since I squared is minus 1, we can combine these two to get minus y1 times y2, plus the imaginary part of this product is x1 y2 plus x2 y1. So this is how we define taking the product of two complex variables. So what does this mean geometrically now? So one of the things we can check for is what is this resultant product, what is the magnitude and the argument of this resultant product. So if you recall the way we define the magnitude of any complex variable, it's the square root of the square of the real part and the square of the imaginary part. So in other words, it's the square root, you take the square root of the square of this, which is x1 x2 minus y1 y2 square, plus x1 y2 plus x2 y1 square. And now we can simplify what this algebra looks like, and maybe we can get rid of this part for now. Okay. So if we simplify this, then we find that z is, or modulus of z is, so we'll just square these quantities. So we have x1 square, x2 square plus y1 square, y2 square, minus 2 x1 x2, y1 y2, and then plus x1 square, y2 square, and then again inside the square root we also have x2 square, y1 square, and then plus 2 x1 x2, y1 y2. So notice that these two factors cancel out, okay, and then we are left with, so we can combine a couple of terms, this with this, and maybe we can get rid of this. So we'll find x1 square, and then we have x2 square plus y2 square coming from here, and then we can combine these two terms by taking a common factor y1 square. We have x2 square plus y2 square. So notice that these two are common for this, so this simplifies further to give us x1 square plus y1 square times x2 square plus y2 square. Okay, now this factor, now if you remember the way we defined z1 was x1 plus iy1, and so modulus of z1 is actually x1 square plus y1 square, and likewise the modulus of z2 will be square root of x2 square plus y2 square. So in the end what we have is the product of the modulus of z1 times, or rather z2, and this product is nothing but mod of z1 times mod of z2. Okay. So through this algebra we see what the modulus of the product of two complex variables stands for, and what this tells us is that the modulus of the product is essentially the product of the modulus of the two complex variables that we are taking the product of. Okay, so the other part that remains is what does the argument stand for. Now, the way we define tangent of theta, and again, if you recall, the product that we calculated was. So again, the product of two complex variables looks like x1, x2 minus y1, y2 plus I times x1, y2 plus x2, y1, right? And now we need to calculate what this argument of this complex variable z, what is it in terms of, let's say, the argument of z1 and argument of z2. So we've just seen that the modulus of the product z is nothing but the product of the modulus of z1 and z2, and now we need to see what the argument is. So tangent of theta for z, which is the argument of z, is the imaginary part divided by the real part. So that is x1 y2 plus x2 y1 divided by x1 x2 minus y1 y2. Now again, if you the z1 is nothing but x1 plus I times y1. So the argument of z1, or tangent of, let's say, theta 1, is y1 divided by x1, and in the same way z2 is x2 plus I y2. And so tangent of theta 2 we can define as, which is argument of z2, is y2 divided by x2. So we can cast this expression in terms of tan theta 1 and tangent theta 2 by dividing the numerator and denominator by x1 and x2. So if we do that, if we divide the numerator and denominator by x1, x2, we find that this term will give us x2 y1 divided by x1 x2, which is which is nothing but, or let's just do it, x2 y1 divided by x1 x2 plus what we're looking for is x1 y2 divided by x1 x2, and in the denominator we'll have this term goes away, 1 minus y1 y2 divided by x1 x2, and so this cancels here, this x1 cancels here, and then what we have is tangent theta 1, tangent theta 2, and then tangent theta 1 times tangent theta 2, and so this is tangent theta 1 plus tangent theta 2 divided by 1 minus tangent theta 1 tangent theta 2, right? And if you recall the trigonometric identity, tangent of theta 1 plus theta 2 is actually tangent theta 1 plus tangent theta 2 divided by 1 minus tangent theta 1 tangent theta 2. So this is nothing but tangent of theta 1 plus theta 2, which is tangent of theta. And so the principal value, like if we compare the two arguments or two angles on both the sides, we find that theta 2, the principal value, is nothing but theta 1 plus theta 2. So this is interesting. So we found two things. First, that given the definition of the product of two complex variables, the modulus of z is modulus of z1 times modulus of z2, and the argument of z, which is theta, is the sum of the arguments of z1 and z2. So what does this mean geometrically? it means that, so let's keep these two results together. So for the moment, we're also not worrying like which quadrant it is. Let's just assume that all theta 1, theta 2, and their sum is in the first quadrant, just to make the drawing simpler. So what this means is, if we have, let's say, the first complex variable z1 like this, making an angle theta 1, and then the second complex variable z2 could be like this, making an angle theta 2, and both of them have different lengths, so their magnitude is different. Then their product is a new complex variable, which we can write as z, whose length is the product of the length. So we can write this as mod of z2, making an angle of theta 2, and this is mod of z1, making an angle of theta 1. Then their product is has a length which is the product of the lengths of the two, and the angle it makes is theta 1 plus theta 2. So this angle is theta 1 plus theta 2. Now another way to state this result is that, which will be extremely useful, as we mentioned at the beginning of the video, especially when we go and study the calculus of complex functions, is that multiplication of two complex variables or two complex numbers leads to two important effects. One is amplification, which means that the length gets scaled. So if we multiply, let's say we multiply some complex number z1 with, we can also do this if you're multiplying it with some constant, for instance. So let's say we're multiplying it with some complex number z2. We can think of this product as taking z1 and amplifying its length by the magnitude of z2. By amplification, it sort of also means that the length could increase or decrease depending on the magnitude of z2. So we can think of this operation as z2 amplifying the length of z1 by an amount which is the magnitude of z2, because the net magnitude is modulus of z1 times z2. So that's amplification, which could mean scaling up or scaling down, which means reducing or magnifying the length or reducing the length. It includes both these effects. And the second effect is a rotation. And this is because if we are thinking of this as an operation that we're performing on z1, so think of this product as an operation being performed on z1 by z2. So z2 is doing two things. It's amplifying the length, and the other thing it's doing is it's taking this angle theta 1 and it's rotating it by an amount theta 2. So a rotation and an amplification are the two effects that we can think of this product. So we can think of this product as an operation being performed on, say, z1, and then we have these two important effects that z2 is causing on z1. We can also invert the process and think of this, because these commute. We can also think of z1 as operating on z2, and again it's the same effect. So if you think of z2 as the thing that we are operating on, then z1 is amplifying its length to give us modulus of z1 z2, and it's also rotating this particular vector z2 by an amount theta 1. And these two are very important ideas to keep in mind, especially when we move on to calculus, as we mentioned before. So I hope this will be of some use, and let's talk a little bit more about. There's another interesting interpretation of what the product of two complex variables stand for in terms of how we relate to the product of two vectors, and let's do that in the next part of the video. So see you there. Thanks.